Okay. So let's try to resolve these exercises for this block. First will be to running SlingTie on the mapped reads, and then we'll be running ht-sec to calculate expression. So let's start with running SlingTie. As I mentioned before, this is based in this protocol that is from Nature protocols that you can find in the files section. And again, once you run SlingTie with each of the samples, I2TA with each of the samples, you take these alignments and you run SlingTie to assemble transcript. You will assemble one transcript per sample, okay? Then you merge all of them, okay? And once you merge all of them, you may use GFF compare to see if you have something different or not. And finally, SlingTie EB just to create the coverage. This coverage will be the input for Bulbo. That is a package just to do quality control, but also expression. We will look into that next day, not today. Okay. So that is kind of the protocol. So here I put some examples. As I mentioned before, with SlingTie, you need to run 3 different sections. First, transcript discovery. Second, comparison. And the final one, quantification. Remember that this tool is going to quantify as FPKMs. Okay. So, as I said, the inputs are going to be the BAM formats and the GFF file with the annotation. So let's go here. Let me, so I have all these my directories. I have everything in mapped reads. Okay, and here I have everything in I2TA. So these are my I2TA BAM files. And the command that you need to run will be something like, as I mentioned before, first we need to modelize these transcripts. So it will be something like SlingTie -p. Let me run this with more cores, let's say 48 to be as fast as we can. That is the inputs. Then, because we want to modelize transcripts, we have a different commands. So -g with the reference, -o the outputs, -l the sample label that we want, and then the BAM. So let's go back here. So -g and let's go to all references. So references, and then here we are going to look for these ports, GFF3, gene transposons, and then GFF should be fine. So that is G, then -o. So the -o should be the same than one of the inputs. So let's say this is going to be 24, rep 1, but this time terminated in BAM. We are going to call this, for example, row SlingTie. So SlingTie could be STG.
So in this case, it's always the GFF file, not the GTF.
You can use both. So
okay.
The SlingTie allows you to use both. Other programs only GTF.
Okay, cool. Because I had the doubt. Okay, thanks.
Yeah. So this will be row SlingTie. And then GTF, because this is one of the outputs. Now we want a label, so the label should have the same name than the input. So let's call this I2TA Arabidopsis thaliana C24 rep 1. And then the final thing is going to be the BAM file. Okay, so let me check once again that this is right. -p, -o, -l, yeah, so that sounds good to me. So if I do this step should be relatively fast. Relatively, as I said, it's not immediate, but and I'm going to run this not with just one replicate, but at least with 2, no? So at least we will have 2 to play with, because if you want to merge and you only have one replicate, one thing, of course the merge will be the same than the inputs, no? So even it's not going to give you an error, it may not have maybe all the sense that it should have. So, okay, so let's see. So this is running with 48. Remember that you are impatient. You always can check with top. I can see a lot of people running HD sec count. I'm running string type. So good. So far, so good. Okay. So the output is going to be a GTF file. So it means that the output that this program is going to give us is telling us where you have transcripts in the genome. Let me back here. Okay. So still is working. So meanwhile, this is working. So how that looks these files? So let me go to the folder where I copy all these things. So I have everything in this separate folder that say transcript models, HiSat, string type raw models, and then you can find these GTF files. So this is how looks these files producing by string type. So as you can see, mostly is a GTF file. And in this GTF file, you have the first column that is the sequence ID, second column, the source of the annotation, this is string type. The third column is telling you what kind of line do you have. So in this case, it's transcript, and each of the transcripts is composed by exons. Okay, then you have another transcript and another exons. If you go to the transcripts, you can see that you have a gene ID and a transcript ID. Okay, sometimes you may have sometimes you have transcripts that may have the same gene ID because you can have alternative splicings, no? So this is how it looks this. And also this program, at the same time that is producing these transcripts, you can see that it's producing coverage, FPKM, and TPM. Okay, even we are not going to use these ones, but they also are producing that. So this is how it looks this GTF file. So this is done. The first is done. So we have the first GTF. So let's run another one just to have also another replicate. Okay. So you see here, no, the output is giving me something that is around 48 megs. Okay, so that's to let you know that that is wrong. Okay, so this is how looks all of this, and of course, if you are running this as a part of the whole process, you should end it with one of those per sample. Okay, so we have for the replicate 1 sample 24, replicate 2, replicate 3. Same thing for the 24 per Columbia cross, or the Columbia per 24 cross. Okay. Then, because this is the file that where I'm doing this, also I created here the merge list and also the string type merge. Okay. You will expect, if everything goes right, you should expect that the alpha string type merge should be bigger than any of the files that you are merging. Okay, that is another important thing. Why you are merging them? Well, because sometimes for some samples, you may have some transcript that doesn't exist in other samples, okay? Especially if you are comparing samples that are too different. So you want to create a common reference. So that is the first part. Once you create the common reference, the question is, how different is my common reference from the reference that I have been using that someone else produced, that is this ARA port 11. And then it's when you use this GFF code compare that I don't know you have the chance to run it. GFF compare will produce this GFF CMP files that you can see here. Then we will take a look. Okay. So once you are producing these GTF files, of course, when you are producing the GTF files, you need to be able to redirect the names of the GTF files into a file that is going to be this file merge that is going to tell these programs, merge list, that is going to tell these programs each of the files. So how it looks file merge should be something like this. Merge list. Okay, so it's just a simple list in which you have each of the GTF files. Of course, you can use them as a relative path, as you can see here, or you can put the full path if you want. It's up to you. Just keep in mind that the files should be in the same directory. Okay, so yeah, this is done. Okay, so if I type that, you see that I have 2 GTF files. So how I can capture these GTF files will be something like ls grep GTF, and then, so well, let's do a step by step. If I do ls, I have this. If I have pipe this in grep GTF, I will have the list of the 2 GTF files. And of course, now if I redirect this into the merge list, this is the thing that I have. Okay. So once I have that, the next steps will be to run a string time merge. Okay. So paste. Let's check that everything here looks fine. I think so. So no, it's a ref GTF. Of course, it's not this one. So the reference GTF will be. And I said you can use GFF if you want. So port 11, GFF3 transposons 2. Okay. If I run this, tell me input file merge list cannot be found. And is because with the copy and paste, I'm pretty sure that there's something wrong. Keep in mind that one important thing. I have run this and this failed. Okay, so yeah, I don't have anything. So okay, so let me see. So my suggestion, because I did the copy and paste, is go and replace this and see if
it's probably because the name in the directory is merged and not merged. There's an additional D.
Okay, okay, perfect. So sorry, at this point I'm kind of tired now. So merge. Okay, perfect. So now it's running merge. And then when you merge, you will have a GTF file. Okay, so you will have this GTF file that with this. Keep in mind that if for some reason you run this and you did the running wrong, and then you run the ls, okay, imagine that you want to run this command again. Keep in mind that because you have now a new GTF file, you will have this string type merge, okay? So you want to avoid that. You want to rerun it. Okay, so we have the merge file. So next steps will be just GFF compare. So the GFF compare will work. So help, as you are curious about all the different options, but it's more or less like I put here. No, you will use -r and the reference, and then the ones that you use at the beginning. So GFF compare here will be string type merge -r 0 references, and then paraport GFF exposures to GFF. So we run this, it's going to start to produce a lot of different files, and then we can take a look at the files, okay? So yeah, it's quite fast. We are not going to look into this output because this was run with just 2 files. We want to take a look of all of everything, no, with the 12 samples. And we want to know also specifically what means each of the fields. So the instructions about how GFF compare works, or the one that interests us, can be found here in protocols. Okay. You have this class code used to describe how assembler transcripts compare with the reference annotation. No. So we would like to see how this is different compared with what we have. So let me go to here. Yes. So I have this GFF to compare files, no? So I can start to look to them. So you have this ref map. You always can take a look at this. You see the list. So here is the list of the reference ID, then the query. So this means the ones that you are producing with the program. And then this code is telling you if it's the same or not. No? So for example, you know that for this gene, you have the same, okay? Then for this one, you have the same. For this one, you have the same. But, okay, so you see that this a MSTG7, so means that you have, so this one, that in the original file are 1, 2, and 3 genes, okay? Here is just one transcript, okay? This MSTR7. So this is the kind of thing that you, of course, need to be careful, no? Because it means the rest looks the same, no? 13 is this one, 23 is 81G01160, so more or less the same. Okay, sometimes you have genes that have been infused. Okay, like this one, but more or less look the same. So we want to know about these equals. One possible option that we have is, let's say, cat-s3 head, and let's check if it is. Yeah, I'm getting the class code. So now you can type this with sort unit.c, and it's telling me that, yeah, this program put equals to everything. So it didn't start to think a little bit about that. I don't know, maybe if, when we run this by default, it didn't went to the analysis. So let's see this T-map, maybe this one. Okay, yeah, T-map looks like is a more complete and detailed analysis. Okay, so let's do the same thing but with T-map, because we will have the information that we wanted. So compare with the original file. Okay, according to this, we have the same 59,000 features, but then we have some of them changed, no? So you always can go to the publication and say, okay, so the predicted transcript is a potential novel isoform. Okay, so we have potentially, we have 9,739 potential new isoforms. Of course, these kind of things are better if at some point you upload with IGB and you see that manually. But again, that is a way to compare. Anyhow, still, I mean, let's suppose that everything is fine. We will need to do the last step. Okay, for the last step, yeah. After the GFF compare, we want to quantify And for that, we need to run this command. Now, by the way, this is not the one that I substitute. So the one that I substitute is this one. Or maybe I didn't produce the change. Let me see. Yeah, this one, because I need to have this sample count. Okay. So we will run this as a string type. -e -b, that is the thing that we need for the quantification, that 48 -b 48, then -g, and now we want to use the merge because we will have a more complete list, the GTF. And then for the output, we want to count this. So the name of the sample, so in this case will be alpha 24 rep 1, because we want to create a directory. It's important to put it in this way, and then you can put the name that you want to the rest. We can put the same if you want. 24 rep 1 count, for example, and then the van. Why it's important to put the directory is because this program will produce the same output, okay? So the same output name. So you don't put in different directories. You have the risk that is going to overwrite the output files. So at some point when you are running this, you should have a directory like this. Okay, so you should have one of the directories for each of the samples, and then inside these ones, you should find this. Okay, so all these files, you cannot change the name, so are going to be the same, but these CTABs files are, so you have the GTF file, and then you have all these CTAB files that contains the information about the quantification, okay? Of course, these are the files that you will be uploading in Volvo, and you can play with that. So at this point, I mean, these files are not easy to read, no? So I just recommend to leave it as it is. Doesn't make too much sense to explore until you upload them in the last step, that is Volvo. So this is still running. So that will be all for the string type. Questions that you may have about this part?
I have a question. Not really in this part, but anyway. So when we do a paired-end analysis, we get 2 files, right, for each sample.
When you do, you have 2 files for each sample. What analysis? Sorry, I didn't hear you.
Paired-end.
Paired-end. Sorry.
Pair-end.
Oh, parents. Okay, yeah. Well, yeah. Yeah, you have.
And
yeah.
So the moment when we merge these 2 files is when we input them in star or HiSat2. Is it correct? Just because. Yes. Okay.
Yeah, when you are mapping.
Okay, thanks. Just because we did a lot of stuff today.
Yeah.
Also, I read just today that using Dreamomatic, you have for I mean for output files for every sample in pair end.
Yeah.
And how can I deal with these 4 files? Can I throw 4 files to star or HiSat?
No.
Okay.
No. So, and that is a good question, because the thing is, when you are cleaning the files, so you have to take some decisions, no? One decision is if the two, because you have pairs. So the thing that happened with Climomatic is, well, the thing that happened with FastQMCF is if this pair fail, you also remove this. Okay?
Okay.
So it doesn't care about anything. I remove this one too.
Okay.
The thing with Climomatic is that if this fail, still keep this one, but in a separate file. So you will have pair 1, pair 2, and then the 2 unpairs that they still may have. But for expression analysis, at some point you need to decide if you want to work with single reads or with parents, but you cannot work both at the same time.
Okay. So I mean, it is not useful to keep for file. I can just throw away the 2 unpaired file.
Yes. Yeah.
Okay. Thanks. I understand.
Okay. Perfect. So this program has run. So as you can see, we can see here the directory, and that will be a matter of repeat this operation as many times as I said we have. Okay. So that is with the string tag. What happened with the other one? What happened with the one that with the star? This is much easier. You only need to run one command, okay? So, and the command that you need to run, and you will receive an error, and some of you probably already saw the error, is that maybe this program is kind of more sensitive to the format of the GFF. But as I said, we need to run this part. So basically, the command that we need to do it is this one. Okay. So let me copy just the first part, and then I know that I need to add my GFF. Keep also in mind that this program is not producing new transcripts. So this is keeping much more simple our system. So we have FBAM, FM union, pos ID, 10, and then here we need our BAM. So let's call this C24 rep 1, then align coordinates. Okay, perfect. And now remember these problems about dashes from, okay. And then the GFF file will be our same GFF that we have at the beginning. References would not be GFF, but GTF. ARA ports, free transposons. No, I'm not going to cheat. So the same one that you have is this one. Okay, and then the final output. No, so we're going to call for the output maybe the same name.
So in this case, the GTF file is mandatory. The GTF extension. Okay.
Because it's not modelizing anything. So of course you can get this GTF with different meanings, but yeah. So we are going to call this GTSec count, for example, count. Something like this. So if I run this, it's going to fail because it tells me that the feature, sorry, because it's not GTF, but GFF. Okay. It works fine. Well, yeah, it works fine. So maybe you're also using a GTF. is when it's failing because it's telling you that you don't have the gene IDs, okay? But yeah, no, it's working fine. Okay, so that is with I2TA count, so you need to do it with each of the files, and that the quantification will be ready. As I said, in both cases, SlimTie and I2TA count, this quantification by itself doesn't have any meaning because they have not been normalized, or it has been normalized, they have not been tested and put in a way that is easy to work with. So it will be in the next step when you do the differential expression, also, and produce kind of a file where you can look for the expression of the gene already. Well, questions that you may have about any of these steps? No question.
Yes, for the next time we have to use TIE with all the samples.
Yes, but one option that you can do is copy my files. Okay, so if for next Tuesday you don't have all the files, don't worry. You can copy and paste. Well, you can copy all my files and then you can play with those. No, so yeah, that should not be a problem.
Okay, thanks.
One question that I have for all of you. Of course, I'm finishing this, and once I finish the course, I will pack all these files, all these scripts. I will put in a forgotten hard drive that I'm not going to take a look until someone asks me to do another of these courses. Do you want to have access to all these files? Because if you do, potentially, of course, one thing is you can copy from the server using FileZilla, but if you want, I can create kind of a clean copy of all the different steps, put it in some specific directory or even in a Dropbox, share with all of you, and you can download them if you think that is interesting for you.
Seems good.
Okay, perfect. Just in case, maybe in the future, 1, 2 years, 3 years down the road, you are going to be the people just teaching this class, okay, in some ways. Okay, remember, for me, teaching bioinformatics and RNA-seq give me a lot of beer long time ago. Okay, free beer. So next, let me stop the recording then, because that will be about this class.